I'm Nick Conkle, and I work together with Ryan Moore and Pedro del Castillo to develop a system model to analyze the hydroelectric footwear. From the design team, we got the input of a CAD model with schematic for how the system works, and a bill of materials that includes enough detail about each component to model them. With that, we created a system model in Dymola. Special thanks to Dr. Chris Paredes, who provided us with the student license. The force of the heel was modeled using a trapezoid waveform, which pushes on the heel sac, modeled as a piston. The water flows through the system, through check valves, modeled as one-directional valves, with a coefficient of loss that was derived using the datasheet pressure versus flow curves. The toe sac was also modeled as a piston, and the tubes are modeled using pipe elements in Dymola. More on the generator on the next slide, but here you can see the volume flow rate, which is measured into the generator, and a table. The generator pressure and flow diagram was used to model the fluid resistance of the generator, and the voltage versus flow diagram that was given in the datasheet of the generator was used to create the table that Dymola references to provide an output of voltage for a given flow. The initial results are shown here. The flow and voltage at the generator agree with the curve from the datasheet. As you can see, the 0.7 liters per minute flow corresponds to approximately a quarter of a volt. However, the voltage is fairly minimal. This amount of flow doesn't get the voltage up into its maximum operating point, above about 3 liters per minute, where you get 3.6 volts. The pressure in the system can also be found. Here's the heel sac pressure and the toe sac pressure, and the pressure drop across each of the 4 valves. When the valve is reversed and no flow is allowed, you have a higher pressure and then a lower pressure when the fluid flows through, or a lower pressure drop when the fluid flows through the valve. But to try to increase the voltage generated by the generator, a few things were simulated. Larger diameter tubes and valves was one parameter. So going from 3/16 inch to half-inch inner diameter tubes and check valves brought the voltage from about 0.2 to 0.3 volts to 3.6 volts, which is its maximum operating area. Cutting the heel sac and toe sac area in half did double the pressure because the force is the same but the area is half as much, but it has less of an effect on voltage generated, and it increases the pressure in the system. To test the robustness, a user with half the weight and double the weight was simulated. The voltage generated for a half-weight user is still relatively good, 3.347 volts. The system pressures do double though, however, for the heavy user, as you can see here. And just to show the voltage generation robustness, this is both the light user curve and the heavy user plotted on the same chart. Note that there is minor variation, and this is with the half-inch tube and half-inch valves. So in conclusion, the design as is would generate little power due to the high flow resistance in the tubes and valves, but larger diameter tubes and valves would reduce the resistance and allow maximum voltage. This design with larger tubes is robust to large variations in user weight, and stress analysis should be performed at the worst case to ensure that the components can take the load. And Lorenz will talk more about that.
Hi, this is Lawrence Goxel. I'll be talking about the stress and fatigue analysis portions. Our purpose is twofold. First and most importantly, to provide a safe product for the customer that can withstand loading they may experience with positive margins of safety. The second is provide a product with the maximum amount of longevity under the worst loading conditions. We start by understanding who will wear the shoe performing what activity. At the end, we will provide a margin of safety based on the external loads the shoe will need to endure. This ties in directly to the component geometries and respective materials utilized. The customer requirements list will mandate the type of loads that need examination. We can build analytical methods and create assumptions based on this. Once we have working constructs, hydraulic pressures going through the system will be generated. These pressures will allow a static analysis on the structure based on respective material ultimate tensile strengths, after which a cyclical analysis will be performed on the component with the weakest static strength, ensuring a lifetime of safe operation. Finally, margins of safety can be generated on all these items that will provide substantiation to the bill of materials. The customer requires the product to withstand a drop from a certain height with a given weight. We can correlate this drop to a certain amount of energy exerted onto the fluid sacs with energy balance equations. Some of the assumptions include treating the fluid sacs as piston-actuated pumps, including all efficiency losses associated. In addition, the stroke of the system is assumed to be correlated directly to the radial displacement of the generator. Depending on the load condition, the operational pressure found in the system ranges from 25 to 115 psi. The main source of failure found in the hydraulic components are hoop stresses, defined by the equation shown. Fluid sacs were found to have the largest such stresses due to their relatively large radius compared to other components. As with the sacs, components that endured the largest loads were analyzed first. Those parts that had similar geometries and materials with less load were qualified by similarity. Fatigue analysis was examined by a Goodman method, which defines an area where cyclical loading will not affect the life limit of the part, as shown on the screen. The static and fatigue analysis performed provide positive margins of safety and a definition for a theoretical life limit. The methods and assumptions, although theoretical, have proven successful for other industries where safety is paramount. Based on these items, we structurally confirm the safety and application of the bill of materials.
Hello, I am Gunnar Bergeson from the prototype team. And for our prototype, we wanted to obviously stick to what is in the design. And in the design of this project, we were supposed to simulate a hydroelectric generator that can function by pushing bladders in two different directions, and that flow will create electricity through a hydroelectric pump. So in order to do that, we decided, or to prove it at least, we decided to prototype it. Now, while all of this is embedded in a shoe, we didn't go to the extent of prototyping the entire shoe with the mechanical and electrical components inside it. Instead, we decided to focus on the key concept of this project, which isn't the shoe itself, but actually the mechanisms in the sole. So, there are two sides to that. One's the electrical and one's the mechanical. And my part of the prototype is involving the mechanical side. And in the design, there are some areas that were changed from the prototype, and we tried to reflect, or that were changed from the patent, and we tried to reflect those in the prototype itself. And these will be discussed as we walk through the different areas of the prototype, and I will explain those for you. Alright, now I will discuss with you the actual prototype itself on the mechanical side and what we chose to purchase and to build in order to simulate the actual design. Over here we have what is designed to simulate our bladder that will be stepped on by the heel or the toe, either one. And this actually is a cut-off piece of a nasal aspirator for a baby. And so this is then adhesively bonded, silicone adhesive bonded to some 1/2-inch inner diameter vinyl tubing. And this tubing is then joined here to plumbing parts. And these plumbing parts are all 1/2-inch tubing. And this is all stuff that was purchased at Ace Hardware, just standard hardware parts. And this is all joined together through a very
a bunch of elbows and T's and various fittings to get everything to chug together. If it looks like it's a little bit sloppy in how it was put together, it's because in order to keep the thing filled with water to test the fluid flow, for the final pieces of it, it had to actually be built in a bathtub. That was interesting. So here, though, are some of the main components of this fluid system. Here you have 4 individual check valves. You can see that these are one-way directional valves for those that don't know what a check valve is. So in other words, water can flow this way through this valve, but it cannot flow backwards. And so there's a system of these throughout the design. And what these do is these direct the water to go one direction through the hydroelectric generator at all times. So regardless of whether you press on this reservoir of fluid or on this reservoir of fluid over on this end, water will always flow this way through the generator. And that's simply because, one, if you're switching the direction that the turbine is going in that generator all the time, every time you step, you're going to lose efficiency. And two, the generator that we chose actually requires a single direction of fluid flow. So the generator here, which is the heart of the entire design, this is the actual generator that was chosen for the design itself. It's the smallest one that we could find, has a single input, single output, which is different than the patent itself. The patent shows a dual input and dual output generator setup. I was not able to find that, nor was anyone else in the class, so that makes the schematic of the tubing slightly different from the intent of the patent itself. But we tried to stick as much as possible to what the patent had. So, as the water flows through here, it goes through the generator and over into this other bladder reservoir. And then once this is compressed, the water flows back, the one-way check valve forces it to go through this path, and then afterwards, this one-way check valve forces the fluid to flow back this way. Since there's still pressure on this sac back here, the back pressure will prevent fluid from flowing again through here, and it'll instead divert through this path, which will lead it back to the other reservoir. So that's how the loop will be completed. And now it's time to give it a test. Alright, now we're going to give it a shot and see if we can actually get this set up to work, or see if there's leaks since it was built in a bathtub. Alright, here we go. As you can see, it's normalizing out to about 3.4 to 3.5 volts. And this setup was designed to steady out at about that exact range per the datasheet. And so with this information showing that that's what's being measured, we can take this now, and the other half of the prototype will be simulated on a breadboard with the electronics that will allow that voltage to then be regulated for use in a USB connection.